Okay, let's begin. Thanks, Markus, for this opportunity, and thanks everyone for being here. For those of you who don't know me, I'm a PhD student at EPFL, which is part of Swiss Finance Institute, and I'm visiting the Bendheim Center for Finance at Princeton University. Let's begin the mini course on deep learning and macrofinance models. Who is this course for? It's for Econ and Orphy grad students and researchers who are interested in solving macrofinance models to study the global dynamics of economic system using deep learning techniques. There are some prerequisites. I assume that you're all familiar with some basic numerical methods like Newton method, finite difference methods, etc. I will not be using finite difference method in this mini course, but familiarity with that will help you in drawing comparison with the neural network. Lots of optimization techniques in deep learning are closer to the Newton method, so familiarity with the Newton method is helpful as well. I assume you've also taken Econ 5 to 9 or equivalent, but that's mostly to solve the macro model, which will be on Monday. For the first 2 days, we will cover basic deep learning techniques for which you strictly do not need Econ 5 to 9. And the tools that I'm going to introduce you to are more general. They can be applied to, in general, any equilibrium model that has partial differential equations. So models in continuous time can be portfolio choice models or models in international finance or any microfinance model. Just for application, on Monday, we will see how to use deep learning techniques to solve a macro model. So in that regard, familiarity with the models that you saw in 5 to 9 would be very helpful. I assume that you have some familiarity with some programming language, preferably Python, but MATLAB and Julia is also okay. The skills are easily transferable. And I will provide some basic slides on object-oriented programming because lots of TensorFlow code are written using classes and objects. Now, object-oriented programming is very vast. That's a course in itself, but we will not cover all of them. All you need to know is basic concepts of how to use classes and objects and why they are useful, as opposed to just using functions. We will use TensorFlow. There are other alternatives as well, like PyTorch or JAX. TensorFlow is relatively old compared to the others, but still it has strong community support. Also, if you are comfortable with PyTorch, it's fine as well. Again, the skills are easily transferable, but I'm going to use TensorFlow too. But you don't have to know TensorFlow now. If you know NumPy or Pandas in Python, then the syntax is going to be very familiar to you, but even otherwise, it's not a big deal. I'll cover the basics and you'll get the basic syntax. All right, so here's the agenda. There are 3 parts. In the first part, I'll introduce you to basic neural networks. In particular, why deep learning is useful as function approximators, and I'll compare them with other existing methods that you might have learned in grad school, for example, projection methods. In the second part, I'll dive into deep learning principles. Deep learning is widely successful because of the optimization techniques that have been developed in the past 2 decades. So I'll spend some time on high-dimensional optimization techniques, in particular gradient descent technique and its variants. I'll spend some time on going under the hood of deep learning with respect to activation functions, parameter initializations, etc. And like I mentioned, a lot of macro models, as well as the deep learning model that we will see in the 3-day workshop, uses classes and objects. So I'll introduce some very basic object-oriented programming principles, but it's just a couple of slides to get your feet wet with respect to classes and objects. We will not talk about inheritance, polymorphism, so on and so forth. Object-oriented programming principles are, it's a very vast topic, and it warrants a separate course in itself. All right, the third part is to solve macrofinance model using the deep learning techniques that we will see in the first 2 parts. If you have taken Econ 5 to 9, then it's easier to jump right into the macrofinance model. Otherwise, what I will do is I'll provide a class library containing the macrofinance model. and you can just focus on how to solve PDEs, assuming that the microfinance model is given to you. Yeah. Okay, that's the agenda, and here are the references. Most of the materials, especially in the first two parts, will be drawn from these materials. A couple of excellent textbooks here, but there are also lots of other sources. I encourage you to take a look at this interactive learning material called Dive into Deep Learning. And there are other slides on the macro part from Jesus Fernandez Villaverde. And there are excellent teaching materials by Hugo La Rochelle and Hitesh Kafka. But for the third part, will be mostly based on the models that you saw in Econ 5 to 9 and my methodology paper. But I will provide the references later for the part 3. All right. So in the first part, let's get right into what neural networks are and why deep learning is helpful as function approximators. And let's compare them with other existing methods. Now, lots of the material in the part 1 is going to be very basic because I'm assuming that you have not seen what neural networks are before. So I'm going to be a bit slow, but I encourage you to ask any clarifying questions, or if you want to draw comparisons to other techniques that you've seen in grad school, I appreciate if you ask them. Okay, let's jump right in. Although machine learning is widely used now, the basic idea of machine learning is fairly old. In fact, Rosenblatt in 1958 introduced the idea of perceptron, which was a very basic function that took in inputs and gave you binary outputs. It was popular in the 60s and 70s, but the progress largely halted during the 90s because it was very cumbersome to train these models. There are 3 big forces behind the revival of machine learning as we know today. First is that lots of data were available. The success of deep learning really hinges on the availability of data. Without large data, it's not possible to train a deep learning model. So the availability of large amounts of data really revived this literature. There are 2 other reasons. Second is that the computational power became much cheaper. Today, we all have access to GPU, even if you don't know them. For example, Google Colab provides free GPU access. You can just open up an account. And in fact, that's what you will do at the end of the lecture today. And third is that success of deep learning is all partly because of advancements in algorithm to optimize in high dimensions. Okay? All of these things kind of revived the literature, and combined with that, there are lots of packages that are being developed in the industry. For example, TensorFlow was developed by Google, PyTorch was developed by Facebook, and there's this huge ecosystem that is being built in the industry, and they're really pushing forward the tools that are available to solve these deep learning models. And these packages, they are really developed by the best software engineers of our generation. So there is a huge scope for improvement in the future as well. And all these things will evolve and will provide economists, lots of tools to solve interesting models using deep learning. Okay, so let's get right into what deep learning is. Now, since we are in economics and in financial engineering, let's think of a function approximation problem. You have a simple function here, y equals f of x, and x is a vector, and y is some scalar. In basic econometrics, this is simply a regression problem, whereas in macroeconomics, f can be a value function, policy function, pricing kernel, so on and so forth. Y can also be a vector, but let's take a simple example where y is a scalar and f is a function where x is a vector of inputs. The goal here is to approximate this function. Let's use an artificial neural network. What is an artificial neural network? It's basically this function here. If you want to approximate this function f of x, what you do is you provide the vector of input x and you multiply them with some parameter wi, and this is called as the aggregation. And figuratively, it is shown here. This is a vector of input x1, x2, and x3, and you pass it into a single neuron sigma. And the sigma is some nonlinear function. Okay? This nonlinear function takes aggregated inputs, where this aggregation is simply x1 times w1 plus x2 times w2, so on and so forth. Okay. This is a very simple aggregation quantity that enters this nonlinear function. This is one way to approximate this function f if the function f is very simple. This is called basically as an artificial neural network at its bare bone minimum. You have a vector of inputs, there are a vector of parameters, you are passing it into a single activation function sigma, and you get the output y. Okay. Why is this useful? Because this is the fundamental unit of deep neural network. Deep neural network is basically some collection of these kinds of artificial neural networks. And that's what we will see in the future. But for now, think of this as the skeleton of a deep neural network. This is how a deep neural network looks like. Now, an artificial neural network only had single neuron. Some terminology here. Let's assume there are n neurons. There are n dimensions of input. There are L-1 hidden layers. All of these are hidden layers. And this is the final output layer. The input layer is usually called as the 0th layer, and the final layer is usually called as the L layer. And the output layer may either contain just one neuron or k neurons. Okay? If you want to solve for a value function, for example, all these data points will come from state variables, and your output will be the value function or your policy function. Whereas in this example, there are multiple outputs. For example, if you want to model some probability distribution, then you would have some multiple outputs. Now, what do we do with this? Each neuron in the hidden layer has two parts. First is the aggregation part, A1A, that's this light blue here. And second is the activation part, which is the H part here. What does it mean? The aggregation part basically takes in all of the input in the first layer, and it multiplies the input with some parameter matrix W, and it produces some output. Okay. Now, remember here that this W is actually a matrix and with dimension n by n. And that's because it receives n dimensions as input, and it has n neurons here. So the moment you see a deep neural network like this, you should automatically think of this W as being, high dimensional. On the top of that, there's also a bias vector coming from here. So this aggregation basically takes in this input, multiplies with some parameter, and adds some bias to it. That's the first part. And it throws some output, and this output is passed into an activation function, H, and that's the second part. Once you apply the activation function, you feed it into the next layer, and you do the aggregation again, and you do the activation again, and so on and so forth. Okay. This is what a deep neural network looks like. In the final layer, you do the same thing. You take the output, you aggregate them, and you pass it into an aggregation function. The activation function in the output layer. This is called as a fully connected feed-forward neural network. Yeah. And this is what we will see in this mini course. There are different types of neural network, and this is the most basic type of deep neural network. Why is this fully connected? Because each of these inputs connect to each of these neurons in the hidden layer. And in turn, the output that comes from each of these layers are connected to each of the neurons in the second layer. In that sense, it's fully connected. Why is it forward neural network? Because if you observe, there is no connection between this neuron and this neuron in the same layer. Okay? And similarly, there is no connection from neuron here to neuron here. So all connections go in a forward fashion, just step by step. In a different type of neural networks, for example, LSTMs or recurrent neural networks that you may have heard of, there are all kinds of crazy connections. There will be one connection from this neuron to here, another connection from this neuron to here, so on and so forth. But here, it's just fully connected, feed-forward neural network, and this is the basic neural network that we will use for this course. All right, so let's see this formally. The aggregation in layer I, remember in this example, there are two hidden layers, one input layer and one output layer. The aggregation in layer I is basically the bias parameter B plus the weight Wi times h of x. And h is simply the activation part. The activation in layer I is simply given by sigma, which is a function that is applied to this aggregated quantity here. So the important thing to remember here is that you apply aggregation, you take nonlinear activation, you apply aggregation, and you take nonlinear activation, so on and so forth.
And the sigma is the same across layers typically?
That's a good question. Typically, the sigmas in the hidden layer are the same. Sigmas in the final layer, the activation function in the final layer can be different, and it depends on the problem. If you want to model some probability, it's usually sigmoid function because sigmoid throws values between 0 and 1.
But I can use different activations in the hidden layer as well. But generally, you're saying that generally it's not that.
Yeah, exactly. You could, in principle, use different number of neurons in each layer, different activation functions, so on and so forth. But typically in a basic neural network, you see the same activation function in each hidden layer, but the activation function in the output layer may be different depending on the problem. And that's why I denote the final activation as O instead of sigma, because typically that's just different from the sigma. Okay. Now, for simplicity, sometimes this is just denoted as AI equals bi plus wi times hi minus 1 without the dependency on x. And here you can clearly see that this aggregation is simply some affine transformation of input, and then a nonlinear activation is applied to this aggregated quantity. Okay.
Well, why is there this bias? What does the bias do?
So the motivation for bias goes back to perceptron. In a simpler setting, you can think of that as like the intercept in a regression problem. Right? And these weights are like the slope coefficients. That's like the analogy. It's not exactly the same, but that's like the analogy. Okay, so in a typical problem, you have data set which has some inputs and some outputs. This can be a regression problem. It can be a function approximation problem. It doesn't matter. Okay? You have some data where you have some inputs and some output, and you want to fit a function using a deep neural network, which I denote as DNN. And this is typically how you denote this deep neural network mathematically. In this example, there are two hidden layers, right? It's easier if you start from the innermost bracket. W1 times x plus b1 is the aggregation in the first layer. Once you aggregate, you apply nonlinear activation function, and that serves as the input for the aggregation in the second layer. And once you have that, that serves as the input for the aggregation in the final layer. And finally, you apply some activation function. Okay. Now, remember that for the deep neural network to work and approximate this function properly, these activation functions, sigma, has to be nonlinear. Okay. Everything else is linear here. The aggregation is like an affine transformation. The only thing that's nonlinear is the sigma. Now, just look carefully at this equation and think what happens if this sigma is linear as well. So then it just becomes like a linear regression problem, right? You cannot exploit the non-linearities in the data. So in a deep neural network, the only thing that's different is that you aggregate and you apply non-linear activation, and you aggregate and you apply non-linear activation in a sequential fashion. All right, in this example, you have lots of parameters, in fact, because each of these W is a matrix, and you have a vector of bias attached to it. And that's why optimization is important in deep learning, because you have lots of parameters here. All right. Now, this is what constitutes architecture. The neural network architecture is the kind of activation functions you use, the number of layers you have, the number of neurons in each layer, and the type of neural network that you have. So I'm just introducing you to the jargons. When people typically say neural network architecture, this is typically what they mean. First, it's a fully connected feed-forward neural network. Second, there are 2 hidden layers. 3, there are n neurons in each hidden layer. And 4, you have some sigmoid activation function. All right. Now, the goal for this problem is that you have to learn the optimal parameters theta using some efficient algorithm. This is what we will see in the second part, but let's take a step back. Yeah.
Just a question. So because I'm applying this nonlinear function sigma to the sum of wx plus b, can I just subsume the b in the sigma, or is it important that I have them separately?
It's important that you have it separately because, well, here you do the aggregation, right? Once you do the aggregation, you pass it into a nonlinear activation, and then you add a bias term. So it's like you're adding an intercept term at each layer.
Also, you learn the intercept, but you don't learn sigma usually.
Sorry, can you say that again?
Don't you learn the biases, right? But
Yeah.
You don't learn sigma. So you pre-specify sigma, and then the algorithm learns the biases.
Yeah.
I'm going to learn how to shift it, not pre-specify how you shift it.
Okay.
Okay.
I'm not sure if I see it, but it's okay. There's more.
All right, so let's understand why deep learning works in the first place. There are many interpretations for why deep learning is successful. One common interpretation is the biological explanation that I gave you before. That's typically how human brain functions. That's for economists, that explanation is not very satisfactory. So let's think of 2 other explanations. First is that deep learning is very good in finding a representation of data that's informationally efficient. I mean, if you're an econometrician, the first point will be particularly attractive to you. There is some nonlinear hidden representation in the data. You want to extract that nonlinear information, and deep learning is really useful in finding and understanding that nonlinear relation. But I think if you're a macroeconomist who's interested in using deep learning to solve for value functions or just use it as functional approximators, then the second interpretation is very useful. Deep learning is actually, what you're doing is that you're applying some series of tensor operations. And when you do that, what ends up happening is that you're changing the geometry of the state space. The change of affine transformations ends up changing the geometry of the state space. And this is helpful because it's much easier to optimize in the simpler geometry. The easiest way to understand this is, let's assume that you have some ball of paper, like I have it in my hand here. It's a crumpled ball, and you want to approximate this function. This is really high dimensional function, and it's difficult to approximate this. If you're a physicist or if you're a computational scientist, you would use Chebyshev polynomial or some Legendre polynomial to approximate, using some really complex basis functions to approximate this ball property. And what deep learning does is that it applies a series of tensor operations to this ball, and it changes the geometry. And the way it does is it first applies a bias term, okay, and it applies some nonlinear activation term, which means that it's rotating. And then it's again applying a bias term, which explains, intuitively your question. And then it applies a nonlinear transformation, and it keeps doing that. And it goes to another corner, it applies a bias term, and it does a nonlinear transformation, so on and so forth, until you just have a flat piece of paper, in which case the geometry of your state space is very simple. And this is a much easier problem to treat. And each application of bias and nonlinear activation function is a very simple operation. Okay? Well, all you're doing is you're just stretching and pulling and stretching and pulling. But what's important is you have to do this sequentially. And lots of times, just stretching once and pulling is not enough. You have to stretch a bit and pull a bit, stretch a bit and pull a bit, so on and so forth, until the geometry of the state space is much simpler, and then you do the optimization. And this is how it's different from the Chebyshev or Legendre polynomials projection methods that you might have seen in your grad school. Yeah.
So are there like theoretical guarantees or like what functions you can approximate? Because you have that with like Legendre or like Chebyshev polynomials.
Yeah, that's a good question. In fact, there's something called this universal approximation theorem that you might have heard of. What it says is that a deep neural network just with one hidden layer can approximate any Borel measurable function. Theoretically, it can approximate any function. It doesn't need to be continuous. It doesn't need to be differentiable even, right? Even if it has jumps, discontinuities, it's fine. It can approximate. Now, experimentally.
Is it with one layer?
Yeah, that's a good question. In theoretically, just one layer is enough, but you need lots of neurons in that one layer. As n goes to infinity, you can approximate. But experimentally, deep neural network is better than wide neural network. The reason we have deep learning instead of wide learning is that it's better to have small number of neurons in each layer and have deep neural network. In an alternative parallel universe, maybe wide learning is the thing.
When theoretically, a Fourier series also approximate any function, you have many other Chebyshev also does. So there must be something special to this. I mean, it's not just the universal approximation theorem is beautiful. It's a Hamana, it's an easy way of application. So is there anything, I mean, this I mean, it's a very simple affine plus some nonlinear activation or regular type of a thing. Just keep doing it. Is there any more insight in there that gives you why this is better than the Fourier, for example?
Okay. I think the idea is that we are trading the parsimony of basis functions with the number of parameters. In a Chebyshev polynomial, for example, I have this equation here, where if you want to approximate this function using Chebyshev polynomial phi, then you have lots of these basis functions and very few parameters. Okay? Whereas in neural network, you have lots of parameters with a simple basis function. So you have this trade-off. And that's why deep learning is much more helpful compared to projection method, because when you have lots of parameters and you have better techniques to optimize in this high dimensional parameter space, then deep learning is much better than Chebyshev polynomial.
Would the automatic differentiation work equally well though with Chebyshev polynomial approach?
The differentiation?
Automatic differentiation.
Automatic differentiation?
Would it work equally well with a Chebyshev polynomial approach, or is it well customized for having a neural network approximation?
So it depends on the kind of activation functions you use. If you use complex activation functions, then automatic differentiation is also costly there. But typically use simpler functions like ReLU activation function, where computing derivatives is like trivial, right? So in those cases, having simpler activation functions is much better. Even though automatic differentiation theoretically works in both kinds of functions, it's just computationally more expensive for Chebyshev polynomial. Okay, to reiterate what I just said, what I have here is a deep neural network that's represented like this. We saw this before. You apply some aggregation, and then you apply nonlinear transformation, and you do this sequentially until you arrive at the final layer. And the parameter vector here is theta, which is actually very high dimensional. And you have lots of these. Each of these guys are matrices, because this one represents layer 1, and this L represents layer L. And these are vectors. And O and sigma are activation functions. If you want to compare that with the projection method, this you might have seen in grad school, where phi I is a Chebyshev polynomial, but there are very few coefficients. Okay. Now, so the bottom line is that deep learning finds the right geometric representation of the state space, where it's much easier to approximate the function, and that's why it's more powerful than the traditional methods. Okay, this is the graphical representation of what I just showed. Now let's go back to the typical problem. The problem is to find the approximation y hat using an artificial neural network. So let's forget about deep learning for now, and let's focus on what this learning is all about. So I keep saying deep learning. We know what a deep neural network is, but we still don't know what learning actually entails. So let's focus on that, but let's focus on a simpler problem here. Now, the moment you see something like this, you should automatically know that you should automatically know the architecture. This is like a trivial artificial neural network, which is one neuron, one layer, sigmoid activation function. Okay? And it has two parameters, weights and bias. Simple problem. Why do we have such a simple artificial neural network? Because the problem that we have is very simple. The goal is to fit these two data points, okay? A trivial problem. That is, at the end of training, so-called training the network, we want to find optimal theta star such that when you plug in 0.5 into this approximation, it should throw you the right output. Okay? Parameter vector theta is WB, and it contains the weight and the bias of the neural network. And the weight and bias are just jargons. You can think of this as slope and intercept or whatever. Now, to understand the performance, we need some metric. Okay? And typically, this metric is this loss function. Once we have the parameters W and B, loss function is simply the mean squared error between the approximation and the actual output. You can also have other types of loss functions. You can have absolute max as the loss or all kinds of loss functions. But for this simpler problem, we have the mean squared loss. All right. So let's do some trial and error and learn. And the reason we are doing this is we want to understand what learning actually entails. Can we try to find W star and B star manually? We have these two data points. We want to fit that using activation function sigma. This is called as the sigmoid activation function. It takes in input in real line and it throws output between 0 and 1. Okay. Now, if you use W, if you set W as 0.5 and B as 0, then this is the function that you get. Visually, we see that this is not a good fit, and we need a metric, and we need a way to determine how lousy this fit is. Okay. How can we quantify that? Well, thanks to our loss function, we can simply plug in the approximated quantity and the output and compute the loss for the two data points. Okay. And the goal in this learning is to make this loss as close to 0 as possible, where as close means in an L2 sense, and that is dictated by this loss function. All right, very simple problem. Why am I doing this? Because let's keep track of the loss. For this W and B, you have loss of 0.07, not good. So let's try some other W and B. Okay. If you set negative 0.1 for W and 0 for B, you're doing worse. Okay. This is the fit that you get, clearly not good. It means that you need to move in the other direction. That is, it helps to push W and B in the opposite direction. Okay. So let's do that. Now, this is a much better fit than before because we are in the right direction, W and B, and we keep doing that until the loss is 0. Okay. We have done this manually, but how can a machine do this? And that's what learning is all about. More principled way of doing this guesswork is what stochastic gradient descent and other variants of stochastic gradient descent method does. All it does is it tries random sets of parameters guided by some principles to arrive at the optimal parameters where the loss is as close to 0 as possible. Okay. Right. Any questions? Okay, let's look at the same problem by inspecting the loss function here. Because there are just two parameters, W and B, we can actually plot the loss function as a function of these two parameters. And what I show here is the guess, and what I show here is the loss computed from that guess. As we keep going, as we use a different guess, the loss is actually increased. And as we move in the right direction, the loss keeps decreasing. And at some point, we reach the minimum, the global minimum of the loss surface. So this artificial neural network, a simple artificial neural network with just one layer and one neuron can approximate this function well. So why do we need deep neural network? Because in actual problems, the loss function looks like this, where you start from somewhere here, and there is some global minimum somewhere here, and you need to navigate through this complex, not complex in mathematical sense, but this nasty loss function in order to arrive at the global minimum. And lots of techniques that we know, for example, stochastic gradient descent and its variants, will help us find this global minimum regardless of where you start from in this loss surface. And that's what we will learn in the next part, and time permits later today. Yeah.
So what is the stochastic about the gradient descent?
That's a good question. If you can hold on to it for a few slides, I will get to it. Let's first do gradient descent and then jump to stochastic gradient descent. That's a good question.
Do you want to say stochastic gradient descent guarantees you're going to find the global minimum, or it helps by trying to find the global minimum? It's not really the same thing.
It helps. It helps achieve the global minimum, right? And the reason it helps is because if you don't have a stochastic nature in how you navigate through the loss surface, you might get trapped in a local minimum. Now, just visually inspecting this complex loss surface tells you that there are lots of local minimum, right? There may be some global minimum here, but there are lots of local minima here. It's very well possible for the algorithm to be trapped in a local minimum, and stochastic gradient descent helps you avoid that. But I will get into this later. Okay, any other questions? Cool. So let's understand why neural networks can fit any function. Like I said earlier, this goes back to the universal approximation theorem by Hornick, Stinchcomb, and White, 1989, which states that a neural network with at least one hidden layer can approximate any model measurable function. It doesn't require continuity or differentiability or anything. Even if you have functions with jumps, the function can approximate to any degree of accuracy. However, it's important to have nonlinear activation function in the hidden layer. Like I mentioned earlier, if you just have a linear activation function, then it's no good. Okay? You will end up keep stretching this ball, and you will not rotate the ball at some point in order to simplify the geometry of the state space. Okay? So aggregation and nonlinear activation, aggregation, nonlinear activation. That's the sequence. One activation function that I showed you earlier is a sigmoid activation function that's commonly used in prediction problems because it conveniently gives you an output between 0 and 1. So if you want to model some probability, then sigmoid is good. But even in economics, if you know for sure that the function that you are approximating is between 0 and 1, if there are theoretical reasons for you to believe that it's between 0 and 1, then it makes sense to use sigmoid layer in the final output. Okay. Another popular activation function is the rectified linear unit, which is a very simple function. It's just maximum of 0 and x. Differentiating this function is very trivial, and therefore this function is often used as a hidden layers. To solve partial differential equations, typically you use sigmoid or tan H activation function. It's slightly more complex to compute compared to this ReLU, but experimentally it works better. Or if you want to work on computer vision problems, then ReLU activation function is much better. Okay. Well, why is that?
Don't know.
So one reason is that when you solve for PDEs, you're not only computing differentiation with respect to the parameters, but you're also differentiating with respect to the state space. So in those cases, it helps to have a smooth activation function in the hidden layers. Of course, I'm not aware of any theoretical result. It's just experimentally, it works much better. Okay, let's think of a simple function approximation problem. Let's try to approximate this one-dimensional function, x cubed plus x squared minus x plus 1. This is how it looks like. We want to use a deep, we want to use a neural network with the following architecture. There is a typo here. We're not going to use a deep neural network. We're just going to use a simple neural network, but we're going to add lots of these neural networks. We'll use a feed-forward neural network with just one neuron, like we saw earlier. but we'll have 6 of them, and we'll add these neural networks in order to approximate this function. And we will use a simple ReLU activation function. Now, ReLU activation function is like this, which means that at 0, there's a kink, right? And we want to approximate this smooth function using that kink. That sounds challenging. How can we approximate a smooth function using a function with kinks in it? The idea is to stack lots of these functions one after the other. For example, you start with this activation function. This is just like ReLU, right? Except that you have some aggregation here. So you aggregate and then you apply activation function. And this is how it looks like. Clearly no good. So what you do is you add this to another ReLU function, where again you aggregate and you apply nonlinear activation. Now you're doing relatively well here, but still way off here. And what you do is you take the output and you add it to another ReLU with again some aggregation here and some nonlinear activation. You keep doing that, and after just 6 operations, you can approximate the function reasonably well. There are still some problems here, so forth, but more or less, it looks pretty good. And the point here is to show that even when you have a ReLU activation function with kink at a 0 point, you can still use it to approximate this function, which is continuous.
There's still kinks. Now there's 6 kinks because of the 6 layers.
Yeah, there are kinks, but this is just with 6 ReLUs, right? You can potentially have lots of ReLUs, and eventually you'll end up approximating this function fairly well.
This kind of illustrates your other answer, right? It's not so easy to then differentiate it with respect to X.
Yeah, that's correct. Yeah.
So here it's just the sum of 6, or each next one takes the previous one as the layer?
It is the sum.
It's
In
just-
fact, in the folder, I do have a function. I do have a code called this function approximation. If you have your laptops, I encourage you to open up your Python. And basically just run this function and plot and see the fit. Now is a good time to perhaps open up your laptop and see if you have Python installed. If not, please do. But if you don't have it, it's still fine, because you can open up a Google Colab account. Okay? It's free. And perhaps I can show you how Google Colab looks like. The reason I'm asking you to open up a Colab account is because we will use that to solve the macro model eventually. So it's still useful. Okay, for the Zoom participants, this is the Colab page. Once you open up an account, you can just open up a new notebook. And in the Dropbox folder, there's a function, there is a file called function approximation. I can just copy the code from there and try to run it and see if it works. I just want you to do this because even if you don't have Python in your computer, you can still use this Colab account and just run whatever you want. You don't need to install Python or TensorFlow in your local machine. You can just do this in the Colab account. So once everyone is done, we can just go on.
Do you need to open to use this account? If you have to have it on your local computer?
Not really, but the one issue is that in this Colab account, if you just have free account, then there are limitations. You constantly need to monitor your web page. If you disappear for a coffee break and come back after half an hour, then it will terminate. Another problem is that you cannot run continuously for more than 8 hours. There are tricks for the for keeping the web page alive. I will post a code in the folder. I think that's very useful. What you can do is you can just view page source, or sorry, what you can do is inspect. Yeah, right. And go to console. And here I will give you a simple JavaScript code, just 4-line code. paste it, enter, and what it does is every 5 minutes, it automatically just moves your mouse in this web page. It's just a way to cheat Colab.
How expensive is it? The Pro account.
Pro account, I think $8 per month. More than
But it's still per minute, it's not that $8.
it's not that expensive, but I'm cheap.
No, I think you put the mouse.
The sign in front of these velo neurons, this is something we're learning that we are imposing from the beginning.
The sign,
Yeah, the I mean, like accounting for this function, you kind of need this. I mean, you need a minus.
yeah, we typically learn that as well, but in this example, I'm just saying,
Imposing it, but like
Yeah,
we would like this one.
exactly.
We would not only learn the shift, but we would also learn the sign in front of each of these.
and also all the parameters here. You see, I have these numbers hard coded. They are also typically parameters.
No, of course, yeah, I see. These are yeah. And when you said before, we had the sigmoid, and it was between 0 and 1, and we like say it's like useful because the function might be between 0 and 1. There we don't give ourselves the freedom of putting a
Here,
different sign, but here we
yeah, exactly.
Like,
Okay, so let's compare this to the other methods. Because there are other approximation methods, even to solve for value functions or quality functions in macroeconomics. So why do we bother with deep neural networks? Here is a brief summary of comparison to other methods. The first thing that you want to know is that deep neural networks can also approximate functions with discontinuities. There are no assumptions about continuity or differentiability. In fact, you can approximate functions with jumps as well. And it can approximate functions in high dimensions. Okay? So let's start with the projection method that you may have studied in grad school. One problem with projection methods is that when you have irregular shaped boundaries, then it's difficult to use Chebyshev polynomial or Legendre polynomial to project them. Every other thing checks out. For example, to a reasonable degree of accuracy, you can also solve 2 or 3 dimensional models with Chebyshev polynomial. It's difficult once you move to 4 or 5 dimensions, but reasonably well for 2 or 3 dimensions. It can also handle lots of data. It doesn't do very well with discontinuous functions, and it can also solve global dynamics. Okay? By global dynamics, I mean, not linearizing around the steady state. You want to solve for the entire state space, right? Like you saw in Econ 529. Right. The second is Gaussian processes. These became quite popular in the past decade. They work really well in high dimensions. There are papers that solve 10-dimensional models in macroeconomics using Gaussian processes. But they don't do really well when you have lots and lots of data. If you want to simulate from the state space and pass on millions of observations, then they typically struggle. And more importantly, if you have kinks or jumps in the functions, then they are terrible in approximating. But it can be used to solve models with global nature. Third set of models is called adaptive sparse grid. I think Smolyak method is something that you might have learned in grad school. They are great, but the problem is once you have non-convex or irregular shaped boundaries, let's say, then it's difficult to use these kinds of adaptive sparse grids. And this is important when you have models with financing constraints or some frictions, and your state space gets segregated into kind of 2 domains with irregular shapes, and you're solving some PDE in just 1 domain. In those cases, then you cannot really use adaptive sparse. So there, deep neural networks are fairly flexible. Right. So there are deep learning techniques can be segregated into 2. First is the simulation-based technique where you draw samples from the ergodic density of the state space. They check out all boxes, but the problem is when you solve models with global dynamics, then it becomes problematic. I'll explain this part in detail later, but in a nutshell, what this means is that the ergodic density really captures where the economy lives in the long run, okay? Which is mostly around the stochastic steady state. Right? So if you use this method, then you're really solving the model around the stochastic steady state. But if you have some macro model where financing constraints are binding far away from the state space, and you want to solve for the functions there, then you potentially can't, because all your training points are coming precisely from this ergodic density, which is around the steady state. That's one major problem with this kind of law. So the last part is the active learning, where you, instead of drawing from the ergodic density, you just draw from throughout the state space. But then it's computationally costly when you scale to high dimensions. So you use some kind of active learning to figure out where the important regions are, and then automatically draw more points from there. And they may not coincide with the state space where the ergodic density sits most of the time. So in that sense, it's different. But I'll spend
fine-tuning, but that in the space as simplest and École.
yeah. So
Or you will go into this next.
I will have some concrete examples to explain what this actually means. But for now, you can think of some model where you have some economic information. For example, in a model that you saw with Markus in Econ 529, there is a region in the state space where fire selling happens, and there's a kink in the policy function. Like the return volatility explodes, right? And doesn't explode, but it jumps. So that's an important part of the state space, and you want to make sure that you have enough samples from around those state space. Eventually, when you have a high dimensional problem, and it's too costly for you to draw samples from throughout the state space. If you have 10-dimensional model, you can't possibly keep drawing samples from all dimensions. So you draw sparse points first, and then you pad these sparse points using these active points, where these active points are really coming from areas where the financial constraints are binding, where fire sale happens, so on.
So what do you mean by drawing? I mean, there is a model that you simulate from. That's what I was referring in my first question. That the data is real data, like let's go out and get it from outside, or you're just simulating the data?
It's simulated, but not from the stationary density. It's just from the state space. Like you have some bounds for the state space, and you just draw points from there.
And in the second one, you're learning where to draw, like doing something like importance sampling.
Yeah.
Okay.
The closest analogy is importance sampling.
Okay.
But here, you have to learn that actively. And why is it active? Because, as I will explain later, there is an introduction of artificial time derivative that makes this whole scheme iterative, which means that from one iteration to the next, you have some room to learn where the active region is. Okay. Any other questions?
Yes, polynomial methods can sometimes be prone to oscillation between grid points, or kind of fluctuations that come off the grid. And so is it like better in that sense? Do we have more stability in the functions that we are or not? Or do you have an experience with that?
So it gives you more stability because you're slowly introducing nonlinearity in the problem. Because of this artificial time derivative, you're basically freezing the PDE coefficients, and then you're just solving some quasi-linear parabolic PDE. And when you do that, you're slowly introducing nonlinearity. So that's why it buys you a lot of stability.
And extrapolation, is there anything known about properties if we want to extrapolate?
So because we'll use some stochastic gradient descent, typically it avoids the problem of overfitting, right? So it also extrapolates well outside the state space. All right, so what are the limitations of deep learning? First is that it requires lots of data to work with. Why is this not a problem for us? Because, like I just mentioned earlier, we're drawing artificial points. Right? We're just simulating points from the state space, so you can just draw as many points as you want. Second problem is that there's no theoretical guidance for choosing the right architecture. So sometimes you have to spend a lot of time hyper-tuning the parameters. Now, what is the architecture? The type of neural network that you use. For the models that we will see, that's fairly straightforward. We will only use feed-forward neural network. Yeah. Second, number of hidden layers. And third is the number of neurons in each layer. And fourth is the activation function. Activation function, tan H, works relatively well for all kinds of PDE problems, so that's also fixed. Number of layers and number of neurons in each layer, are hyperparameters, and there's no theoretical guidance for you to choose. Typically, like I said, it's recommended that you use deep layers instead of wide layers. What does it mean? Let's go back. This refers to the depth of the network, right? And this refers to the width of the network. Universal approximation theorem tells you that as long as you just have at least one hidden layer, and as the number of neurons in each layer goes to infinity, then you can approximate a function, any function. But then experimentally, it's better to have deep neural network, which is why we have deep learning and instead of wide learning.
But that's, you don't experiment by hand, you try this or try that, or is it like there's an algorithm you can automate something layers?
So yeah, that's a good question. So there's something called hyperparameter tuning. What you typically do is you have some grid where you start from 5 layers in each neuron, 5 neurons in each layer to 1,000 neurons in each layer, and you optimize in this grid. You basically repeatedly solve the model for many number of points in the grid, and you find the one that gives you the lowest training error. Right. Now, what is the problem with that? Is that the learning can be very slow. It can be painfully slow. If you're solving a one-dimensional model, which we will see hopefully tomorrow, then it can be orders of magnitude slower than finite difference methods. But where it helps is when you have a high dimensional problem, which you cannot solve using finite difference methods. By high dimensions, I don't mean 500. Even in 3 dimensions, when you have cross-partial derivatives entering the HAB equation, like you typically have in macrofinance, then it's notoriously difficult to use finite difference methods and achieve convergence. Okay. In those cases, deep learning can be very helpful because the computational time doesn't grow linearly, grows less than linearly. And especially if you have some high performance cluster, it's even better. Why? Precisely because you're going to use TensorFlow, PyTorch, and JAX. They are really optimized for GPU. And that again goes back to my initial motivation for why deep learning is the future. It's because you have an army of software engineers building these tools for you that are compatible with GPU. Because if you want to just use NumPy or Pandas, then they are not compatible with GPU, and it's difficult to use finite difference methods just before. In principle, you can also use finite difference method on TensorFlow, but that's not what the community is going for. And in the future, lots of TensorFlow libraries will be particularly for deep learning, okay? And that's why this is important. Okay, so software requirements, at least for the next part. If you have Python, it's great. All you can do is just open up a spider and just run your code here. But if you don't have Python, then you can open up a Google Colab account. We will use TensorFlow 2. If you want to use PyTorch, that's fine as well. But I don't have the PyTorch code for solving the macro model, but I can show you the syntax and equivalence, and you can translate them. It's not a big deal. We will also use Keras. What is Keras? It's basically a wrapper that makes your life easier in coding TensorFlow. It's a high-level API. If you want to code neural networks using TensorFlow, then it typically takes, if you want to have like 10 hidden layers, then it takes like 5 or 6 lines in TensorFlow. Whereas if you use Keras, it's basically just 1 line. It makes your life easier. Other than that, it's no big deal. And if you have access to a high-performance cluster, it's fine. But otherwise, it doesn't matter. In this class, we are going to solve 1-2-dimension models at best. And for that, you can just use Colab and run it. Okay. But if you have some 3 or 4-dimension models, then I can provide some code in the folder that allows you to interact with some cluster that you may have at Princeton or outside. There, I will show you how to interact with the GPU and send your jobs and get it done and get the output. All right, so that's the first part. Have any questions? Yeah.
So is there any advantage in using like TensorFlow and not Keras?
Is there any advantage?
Using directly TensorFlow and not.
I prefer using TensorFlow because it gives you a lot more freedom, in the sense that it gives you a lot more control as well. I will explain how deep learning in TensorFlow works. When in MATLAB, when you add two vectors a plus b, then the computation automatically takes place. Whereas in TensorFlow, when you add a plus b, then memory gets allocated, and finally you run the session by passing in data. Okay? So how it works is you build a large computational graph in the memory, and then finally, when everything is done, you press a button and you run it. And this is different from how things typically work in MATLAB or Stata, for example. If you use Keras, then you have limited control of how to create those graphs and when those graphs get executed. If you use TensorFlow, then you have a lot more control. Yeah. You can really freeze some part of the graph and run only the other part, so on and so forth. It helps you in debugging. But other than that, they are fairly simple.
Can I ask a couple of questions? Able to hear me? Hello.
Yes.
Okay, great. Thank you. So I just thank you for the talk. So a couple of questions. So one is I find that the description of the simplifying the geometry of the data manifold interesting. But is there a theoretical basis for that? Do we know that it is not actually distorting the geometry further? Somehow, especially given these kinks. I mean, from your explanation, I can see that it actually the kinks are going to lie in a measure zero set. But still, just curious if if there's a theoretical basis for that intuition.
Yeah, that's a good question. I'm not aware of a theoretical result. That doesn't mean there isn't one. But it's just an intuitive explanation that I just find appealing, especially for economists. But there could be theoretical guidance. I'm not aware of it. But if you come, just let me know. I'll be happy to learn.
Sure. Yeah, thank you. Another question is, I mean, if you work with, say, projection methods or something, so typically, when you see an error, you have simple handle, like either increase the number of collocation points or number of the basic functions. But with this methodology, how do I know? I see some error, I see some residuals. How do I know if it is because I don't have enough data, or is it because I don't have enough parameters? Because it looks like if I keep increasing the parameters, it'll just memorize the whole thing, right? I mean, it just feels like that.
You're right. It feels like that, but it doesn't happen that way. The reason is when you increase the number of parameters, you run into all kinds of problems with respect to vanishing gradients.
Oh, I see.
So there is an optimal amount of parameters that you need to use. And what is the optimal amount? Again, goes back to the problem of hypertuning.
Oh, okay.
So the model repeatedly over a grid, and you just optimize and find the right architecture.
Okay, got it. And my last question is when you say about the local minima and global minima, I mean, it felt like, there's going to be many local minima, but there's only one global minima. Is that true, or is uniqueness, do we know that there is some sort of uniqueness, or if we could have multiple global minima, then are they equivalent? Just curious.
It's hard to tell if there is a unique global minimum. I think the way I approach in solving these macro-finance models is in really solving a simpler model where we also know the analytical solution, compare, and then scale it up.
Oh, I see. Okay, there is one. Okay, got it. Some intuition about the model that we already know. Okay, got it. Thank you.
Okay, any other questions? So we are a bit early. We have two options. One is to continue with the next part or wrap up here. So it's up to you. We're all smiling, so it means we wrap up.